while we're talking about command line arguments and memory, there's two more assembly examples that I want to do. The first one involves command line arguments, and what it's going to do is it's going to compare two numbers that are passed on the command line. So here's our pseudocode. So you'll remember we have our command line arguments come into the main function as arguments. So int argc, char pointer, argv, array. So if we're going to compare 3, 5, then 3 is going to come in here, and 5 is going to come in here. Remember that argv0 is the string /compare. That's the name of the program as called. So to get the first user argument, we do argv sub 1. To convert that from a string, which is how we get it, to a long integer, we can use the a to l function. If we go ahead and check man3a to l, it'll say that a to l converts the initial portion of the string pointed to by the pointer to a long. So this gets us the first user command line argument as a long, accessing argv2 and then calling a to l on that is going to get us the second one. Then we want to compare them, and then we want to print which thing was bigger. This is an assembly program. We'll start off with global main. Then we're going to do text. Then we are going to have our main function. Main ret enter 0, 0. Leave. We've got some variables. We want to figure out where they're going to go. The variables that we want to keep track of are argv. We want to keep track of AA. We want to keep track of BB. Let's not worry about argv quite yet. We want to keep track of AA and BB. Now we have this question of, can we just allocate AA and BB to temporary registers? Or do we need to worry about calling conventions and having registers survive across function calls? First thing that we do in our program is call a function, the a to l function, which is going to do that conversion of a string to an integer. And so we need to, for example, here we assign to AA. Then after we assign to AA, but before we use it, we call a function, the second call to a to l. Therefore, at least AA needs to be stored in such a way that it will survive a function call, which means we can't put it in a temporary register without doing our caller save procedure. And we don't want to do caller save, that's annoying. So instead we're going to use safe registers. Now, why did I say that I wanted to save argv? Well, the reason is because argv is a variable. Argv is a variable. And it's in fact a variable that's a function argument. By default, it's going to come in RSI because it's the second function argument. And therefore, as soon as we call a to l, that temporary register is going to get clobbered. And therefore, the second reference to argv is no longer going to work. So we want to save off that argv value in a safe register. We're going to store it in arbitrarily R12 is another safe register. Now, we've saved 3 safe registers, so that's going to move the stack by, or we're going to save 3 safe registers. Let's actually do that. So push R12, push R14, push R15, and if we're going to push, we have to pop in the opposite order. So pop R15, pop R14, pop R12. So we pushed 3 registers. Pushing twice leaves us aligned. Pushing a third time leaves us unaligned. So we're going to have to enter 8 in order to end up with our stack properly aligned on a 16-byte boundary. Now, the first thing that we're going to do is we're going to move RSI into R12, because that's what it says we're doing up here. Next, I want to compare 3 to RDI. If RDI is 3, then we can go ahead and continue. Otherwise, we have a problem. This program wasn't used as intended, so we're going to go ahead and say puts, and we're going to mov usage into RDI and call puts, and then we can jump to done. We'll return 1 from main because that's an error. In the fall through case, we're going to move 0 to RAX so that we return success. And now we have strings, so we're going to have a data section, and we're going to say that usage is a string usage compare to numbers. So if we've gotten down to main compare, that means we had the correct number of command line arguments, and so we can start actually doing the body of this program. The first thing that we do is we're going to call A to L. So we want to mov argv sub 1. So argv is R12. Argv is an array of character pointers. Each character pointer is 8 bytes. So argv sub 0 would be a 0 offset from R12. Argv sub 1 is 8 times 1 is 8 bytes from R12. Remove that into RDI, and we can call A to L, and then we can mov the result of that into R15, because that's our 14, because that's where our AA variable is. Similarly for BB, except BB is coming out of argv sub 2, so that's argv plus 2 times the size of a char pointer, which is 8. 2 times 8 is 16, so our offset is 16, not 12. So this is argv sub 2, given that size of char pointer is 8. So now we have our 2 AA and BB in safe registers. Now we can do our compare of R15 to R14. Remember that compare is flipped because we're doing AT&T syntax. So the question that we're going to ask now is R14 greater than and just, I don't need to have the conditional jump and then the unconditional jump, but this makes it like very clear what the flow is, so I don't mind doing it either. So if our thing is big, then we want to have the message be big. Sorry, SML. So here we are going to put a different string in RAX depending on whether it's big or small. So the, in fact, let's call this greater than, and this less than or equal to. So greater than is going to be the string greater than, and less than or equal to is going to be the string less than or equal to. So now our message for the printout is going to be the string, a number, a symbol, a number, new line. Then to print, we're going to mov the message into RDI. We're going to mov R14, which is our AA, into RSI. We're going to move RAX, which is our comparison symbol, into RDX, and we're going to move R15, which is our BB, into our fourth argument register. Quick, do you remember what the fourth argument register is? Yeah, our CX. Then we move 0 to AL, and we call printf. So that should be a complete program. Let's go ahead and see if it works. No pi o compare.s. Undefined reference to main. I forget to say global main. I said global man. That's not what we need here. Okay, I called them LE message and GT message. Let's just do the thing that I typed, which is less characters. Now it compiles compare. I get a usage message, compare 4 to 5. 4 is less than or equal to 5. 5 is less than or equal to 5. 6 is greater than 5. Our comparison program works great. So that was example number 1. The next example that I want to do is talking about data directives. So if we want to define global data, we have some syntax that explicitly does that. So I'm going to say global main. We're going to have a text section. We're going to have a main function. Enter 0, 0, leave ret. We're not doing any tricky stack stuff here. Instead, we're going to do some of this. We're going to say that foo is space 24 zeros. So this is going to allocate 24 bytes of zeros. And then we're going to say bar is the int 10. And then we're going to say baz is the int 20, the int 30, and the int 40. So these data declarations, or data directives, just put values into memory. So int is a 32-bit or 4-byte integer, and these are going to go in memory right next to each other. So if that's true, that means that the address referenced by bar, which is where the int 10 lives, and the address referenced by baz, which is where the int 20 lives, should be 4 different from each other. So let's go ahead and say mov the address of long format into RDI, and then we're going to move the address of bar into RSI. Then we're going to call printf. So we're just going to see what that value is. That's not the right thing. I need data.bigs. So I run data, and we get some number. Now, this isn't a very convenient number. That's what some memory address for the data section of our program is going to look like. And then we have another complication. So if I just change this to be baz, and I run data, oh, it happened to work. So this is exactly the same prefix. This is 4 bytes later, and that's partially to do with the fact that I specified no pi. If we weren't specifying no pi, then these executables would be loaded into memory in random places. But because we aren't doing that, we get a consistent place, and we can see that these are 4 bytes apart. But just to be absolutely clear, I'm going to mov baz into R9. I'm going to mov the address bar into R10. I'm going to sub R9 from R10, I think is the order. And then we're going to move R10 into RSI here. So what this should print is 4, unless I messed up my stuff. We get -4. I got sub backwards. So we want to print out R9 here. Alright, so there we get 4. So sub is subtracting, baz is the bigger number. So we're subtracting the smaller number from the bigger number and putting it in the place where the bigger number was. Those two things are 4 bytes apart as expected. Let's go ahead and do the same thing for foo and bar. So bar should be the bigger number. And then foo should be the smaller number, and we should get 24. We get 24. You can see how this works. If I go ahead and load the value at bar, so rather than loading $bar, we're going to move bar into RSI. That's going to give us the value at bar, which is 10. The value at bar is... There's a complication. So we need to move a smaller value here. If I just say mauve into RSI, what's happening is that it's going to try to move a value the size of RSI, which is 8 bytes or a long integer. I want to move a smaller value, so I'm going to specify mauve D, I think, for a double word, into ESI. That's the 32-bit version. Before that, I'm going to move 0 into RSI just to make sure that we don't have anything in those top bytes. And now once I do that, or move D, move W, that should be a word. Operand size mismatch. I don't remember what the suffix is. We can get the suffix correct. Since I'm using the ESI register, it's going to move 32 bits, and it's going to correctly print 10. If we were to do the arithmetic, we would discover that this number is what you get when you string a 10 and a 20 next to each other. The one more thing that I want to do is I want to move the address of bar into like RAX, and then I want to move 0 RAX into that ESI register. The address of bar, yeah, that's correct. So with a 0 offset, we get 10. With a 4 offset, we're going to be treating bar as an array and doing bar sub 1, since size of int is 4. We get 20. Note that this procedure of where things are allocated in memory doesn't care whether we put labels here. Accessing bar as an array doesn't care that we also have a name baz for the second element in that array. So I think that's what I wanted to cover about data directives.